Hello, everyone. Today I have my presentation on facial recognition with convolutional neural networks and FPGA acceleration. Deep learning for facial recognition, neural network acceleration on FPGA hardware, and accuracy of AI with real time speed. This presentation explores how convolutional neural networks are used for facial recognition, how FPGAs can accelerate these calculations, and how CNNs offer great accuracy, but since they require a lot of processing, FPGAs allow these models to run with low latency and lower power consumption through the optimization of architecture in these systems. The combination of both technologies powers edge computing in smart cameras, robotics, and embedded systems. Why does facial recognition matter? It's used in telephone security and access, it automates identity verification, and in smart cities and in vehicles, it enables the whole infrastructure. Facial recognition has become the central application of computer vision. It facilitates the passwordless access and improves the user experience, facilitating the functionality of sectors such as banking, transport, and security that are increasingly dependent on this technology. The demand for a fast and reliable system continues to increase. What is a CNN? It's a neural network specialized in imaging. It learns spatial patterns automatically. It uses filters, activations, and deep layers. A CNN is designed to process images efficiently. Instead of programming manual rules, the network learns from pixels. The first layers detect edges and textures, while the deep layers recognize the complex structures, striking out features and defining the characteristics of an image into a final vector that can then be identified and compared. This makes CNNs very powerful for ranking and recognition. Facial image input. The image is resized to a fixed size. The RGB values are normalized and then is sent to the first convolutional layer. Normally, an image is three RGB values multiplied over the entire span of the image in a matrix representing each square a pixel. Before processing, the facial image is prepared for the network and it is usually set to a standard resolution where the color values are normalized, thus improving training and inference stability. The CNN will focus on facial structure and not on differences in scale due to these characteristics. The convolutional layers. They're small filters that scan the image, detect edges, lines, and textures, and generate feature maps based on these characteristics. Convolutional layers apply a filter, usually sometimes some thought of as a small matrix applied over a larger matrix, iterated several times with a stride. A filter can detect vertical lines, corners, and contrasts, with many filters working in parallel, producing different activation maps, resulting in the results feeding into deeper layers. Activation functions. They introduce nonlinearity, with the RELU as the most common, allowing you to learn complex patterns. Without an activation function, a deep network would just be a linear combination of operations, and the RELU removes negative values and keeps positive values. These allow for complex relationships with an image to be modeled. It is simple but a fundamental layer. Pooling layer. It reduces spatial dimensions. It retains important features and the computational cost is decreased. Pooling basically summarizes the information from small regions, with max pooling selecting the highest value of each block, reducing the memory and required operations, and it helps tolerate small movements or changes in the position of the face, thus identifying only the key aspects of the specific feature. Hierarchical learning. The initial layers detect edges, the middle layers detect eyes and nose, and the deep layers identify people. Convolutional neural networks learn from hierarchical representations, first detecting basic patterns and then recognizing larger facial components such as eyes, mouth, and nose, and learning the unique relationships between these features to distinguish one person from another. Fully connected layers. They combine the extracted features and generate the final probabilities of what is being identified at the moment. And after the convolutional layers, the information moves into these dense layers. They combine all the characteristics, and the final output is a represented identity vector where they can be compared and classified. This is the main point of classification. So, the training of the convolutional neural network uses a base of a database that is tagged, and it uses backpropagation, and it improves across various iterations, usually taking a long, long time to train. It require millions or thousands of images, and it compares errors and adjusts internal weights. This process is repeated several times, and the training is very expensive and costly. The real challenges are lighting variations, changes in angles and poses, and goggles, mask, or occlusion in real life. So in the real world, presenting these difficulties, a person may appear turned, shadowed, or out of focus. Objects such as glasses or masks hide key features, and that is why it is trained with diverse data. Why hardware acceleration? A convolutional neural network requires millions of operations. A CPU may be insufficient, but edge devices need efficiency. So a CNN can perform lots of multiplication and addition. In real-time systems, a CPU can fall short, and these many devices have to respond quickly and with low power, and that's where the dedicated acceleration from the architecture in an FPGA will come in handy. So what is an FPGA? An FPGA is reconfigurable hardware. It offers immense massive parallel processing opportunities and customized low latency. It contains several programmable logic blocks, memories, and digital signal processing drives. Unlike a CPU, it can run many operations simultaneously. In addition, the data flow can be designed specifically for a convolutional neural network. This makes it ideal for an embedded AI. CPU versus GPU versus FPGA. CPU is a flexible control, the GPU is a high parallel performance, and the FPGA is offering an efficient custom pipeline that will allow you to take advantage of the low latency and low power consumption that edge AI computing requires. Each platform has a different advantage. The CPU is excellent for general control, the GPU optimizes in training and large batches, and the FPGA excels in low latency inference and controlled consumption. So, a pipeline of a CNN and an FPGA, where every layer becomes a stage and there's a continuous flow of data, also with multiple active layers simultaneously processing information with exploiting the parallelism allowable through the architecture. This pipeline allows different layers to work at the same time. While one image enters convolution, another may be in pooling and another in classification. This greatly increases throughput and is an essential advantage of the FPGA. So partitioning techniques include partitioning by the layer, partitioning by the channel, and partitioning by the different types of filters that are processed through it. CNN computing can be divided into multiple parallel modules, with some architectures separating entire layers, others input channels, and others individual filters. This improves concurrency and speed with successful partitioning depending on available resources. So the memory bottleneck is also an issue where feature maps are great and local cache improves important performance. Many times the main problem is not calculation, but memory. Reading data from external DRAM consumes time and energy, and saving the intermediate results to internal memory speeds up the system. Memory design is critical. DSP blocks. They're integrated multipliers, ideal for multiplication accumulation operations, and perfect for convolution. So the DSP blocks are like the horsepower of your FPGA, where you can adopt and integrate deeper neural networks if you have more DSP blocks. They allow for high performance without the use of too much general logic. Quantization. They're converting float to fixed, lower memory usage, and increased calculation speed. With many FPGAs and accelerators using fixed point numbers instead of floating, reducing data size and hardware complexity. And if done correctly, the loss of accuracy is small. It's a key optimization. Variable accuracy. Different layers use different bits. Smart resource savings and balancing speed and accuracy is important, since not all layers of the CNN need the same numerical precision. Some require more bits and some less. This allows you to save logic without affecting accuracy too much. It is an advanced design strategy. Residual networks allow for deeper models, better accuracy, and more complex data flow. So by allowing direct connection between layers, you can train deeper networks with better performance. In FPGAs, implementing these additional paths requires careful design, but it often justifies the benefit to complexity. Real-time video. With continuous camera processing, frame-by-frame detection, and immediate identification, many systems use live video instead of static photos, and hardware must be able to process constant streams without stopping. FPGAs are ideal for streaming workloads since it entails intelligent surveillance and automatic access. The importance of latency. Doors should open fast, security requires immediate reaction, and it improves user experience. So latency measures how long a response takes. In authentication, nobody wants to wait for several seconds. In robotics or vehicles, delay can be dangerous. That's why low latency is a priority. Energy efficiency. With lower consumption than GPU in most cases, it is ideal for edge AI, reducing heat and costs, with the energy consumption being a limit on many AI projects, including batteries, ventilation, and temperature, all affecting feasibilities. FPGAs usually offer a good performance per watt ratio, which is key in industrial and mobile systems. In the case of design, it's a question of accuracy versus speed, resources versus parallelism, and flexibility versus efficiency. There is no perfect architecture. More precision consumes more resources, more parallelism accelerates and occupies more area. Engineers are constantly balancing these factors. In terms of use cases, intelligent access control and industrial identification and commercial analytics are all examples of the ideal use cases of this technology. And the CNN and FPGA combination has clear applications, with smart buildings, factories, and businesses all being able to capitalize on this. Future trends include smaller models, hybrid CPU and FPGA systems, better automatic tools. The future points to more compact AI running close to the sensor. Hybrid systems will mix CPU for control and FPGAs for acceleration, and new tools will simplify the development of these optimized tools. This will expand the enterprise adoption and the ability for FPGAs combined with CNNs to impact the global workspace. The risks and ethics are the facial data privacy, the algorithmic bias, and the need for strong security. Facial recognition can be used responsibly. Sensitive data requires strict protection and is important to avoid bias in training. Technical success is not enough without ethics. The conclusions are that the CNN has revolutionized computer vision, FPGA accelerates inference efficiently, and together they enable the AI in real time. FPGAs allow these CNN models to run quickly and efficiently, creating powerful solutions to real world problems. They are a strategic combination in the future. Thank you very much, and if you have any questions, please feel free to reach out. These are my references.